Key range partitioning creates hotspots whenever writes cluster around a particular key range and sequential keys like timestamps cluster by definition. The fix is to destroy the ordering relationship before partitioning. Hash partitioning runs each key through a hash function and uses the hash value to determine the partition. A good hash function takes skewed data and distributes it uniformly. December 31, 2012, 23:59 and 59 seconds and December 31, 2012, 23:59 and 60 seconds look completely different to a timestamp partitioner, but their hash values are spread evenly across the partition range. The sequential structure of the keys is gone. Cassandra and MongoDB use MD5 to hash keys. Voldemort uses the Fowler-Nolvo hash function. The specific hash function matters less than its uniformity and its speed. Once you have hash values distributed across a range from 0 to 2 to the power of 32-1, you divide that range into partitions. Partition 0 owns keys whose hash falls in 0 to 2 to the power of 32 divided by n, partition 1 owns the next segment. And so on. The book notes that Cassandra and Ryak use the term consistent hashing for this approach, though the book argues that this term is confusing and overloaded, since the algorithm described in the original consistent hashing paper uses a different technique involving random placement on a ring. Hash partitioning solves the hotspot problem for evenly distributed key spaces. But it destroys the range query efficiency that key range partitioning provides. If you want all records with keys between A and B, in a hash partition system you have no idea which partitions hold those records, the hash function has scrambled the key ordering. A range query must scatter to every partition and merge the results. This trade-off is inescapable. You can have efficient range queries, or you can have even right distribution, but the same partitioning strategy can't give you both. Cassandra's compound key design is the most elegant production solution to this tension. Cassandra's approach to the range query versus even distribution dilemma is one of the more elegant design choices in production database engineering, and it's worth understanding in detail because it shows a clean way to get benefits from both strategies simultaneously. Cassandra supports compound primary keys made up of two parts. The first part is the partition key. Cassandra hashes the partition key and uses it to determine which partition holds the row. This provides even distribution and prevents hotspots on the partition key dimension. The second part is the clustering key. Within a single partition, rows are sorted by the clustering key. Range queries on the clustering key within a partition are efficient, the data is physically ordered. Here's how this plays out in practice. Suppose you're storing user activity events. The partition key is the user ID. All events for a given user are hash partitioned based on user ID, so activity for different users is spread evenly across nodes. Within each user's partition, events are sorted by timestamp as the clustering key. A query for all events for user 123 between March 1st and March 31st hashes user 123 to find the right partition, then does a range scan by timestamp within that partition. This design is specifically optimized for the access pattern. Get me all events for this specific entity, in this time range. That's a dominant pattern in many real applications: activity feeds, sensor readings, audit logs. Cassandra's data model essentially requires you to design around your access patterns from the start, which is exactly the right discipline for a system at this scale. The constraint: you can only do efficient range queries within a single partition. Cross-partition range queries still scatter across all partitions. If you want all events between March 1st and March 31st for all users, Cassandra has to hit every partition. Hash partitioning distributes load evenly when the key space is uniformly accessed. But some keys are inherently hotter than others, and no hash function can help with that. The book describes what the engineering community calls the celebrity problem, or the hotkey problem. On Twitter, a tweet from Justin Bieber gets read and written to millions of times. On Reddit, a post on the front page gets tens of thousands of comments per hour. On an e-commerce site, a flash sale on a popular item generates a burst of concurrent writes. No matter what hash function you use, all those operations map to the same key: Justin Bieber's user ID, that specific post ID, that specific product ID. A hash function just determines which partition owns that key. It doesn't distribute the operations across partitions, because they're all for the same key. If a single key generates enough load to saturate a partition, you have a hotspot that partitioning alone can't solve. The most common technique is application-level key spreading. Instead of writing all operations for user Justin Bieber to one key, you split writes across 100 different keys: Justin Bieber _00 through Justin Bieber _99, chosen randomly. Now those 100 variants spread across 100 partitions or more, and the write load distributes. The cost: reads now have to query all 100 variants and aggregate the results. The application must track which keys have been split, and apply the splitting selectively, not to every key, since most keys don't need it. This is extra application complexity that the database doesn't handle for you. The book is explicit. As of its writing, most databases leave this problem to the application. There's no general automatic solution. The hotkey problem is a reminder that partitioning distributes load for typical access patterns, but outlier access patterns, heavily skewed real-world data, require application-level mitigation.